Following presentation on ultrasonics is produced in association with IEEE, Ultrasonics, Ferroelectronics, and Frequency Control Society, and the University of Houston. This presentation will cover ultrasound around us, what is ultrasound, how does ultrasound work, how to produce ultrasound, and applications of ultrasound. First, we must ask, is ultrasound all around us? How far away is it, and how will we detect it? What is ultrasound? Ultrasound is a blend word that combines the Latin root ultra, meaning beyond, and the English word sound. Sound waves with frequencies above the audible range, i.e. around 20,000 Hz, are considered ultrasonic waves. The chart below shows a range for human hearing and how it compares to ultrasonic waves. Before we dive too deep into the properties of ultrasonics, we need to talk a little bit about waves. Two important wave categories, longitudinal and transverse waves, shall be discussed here in a minute. It is also important to note the speed of sound is dependent on the properties of the media through which it is traveling.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
It is also important to understand the mathematical properties of waves. Here we see the progressive wave displacement equation, where y is the displacement, a is the amplitude, that means the size of oscillation, omega is the angular frequency, t is time, k is the wave number, and x represents a fixed position. Other important quantities are the wavelength, meaning the distance between wave peaks, the frequency, which is the inverse of the time period for a wave, velocity, energy, and intensity. Intensity correlating with how loud we think a wave will sound. We must also discuss wave propagation. There are two types that we will discuss here. Body waves, which are waves that propagate inside an object, and surface waves, which are waves propagating along the surface of a medium. Body waves can break down into longitudinal waves and transverse waves, whereas surface waves break down into Rayleigh waves and plate-Lamb waves. Both types will be discussed in further detail in the following slides. Here is a longitudinal wave. In a longitudinal wave, the direction of propagation matches the direction of oscillation, whereas in a transverse wave, the direction of propagation is perpendicular to the direction of oscillation. As we can see, the amplitude of the wave decreases the deeper into the medium it propagates. Here we see a plate-Lamb wave. Plate-Lamb waves occur for a thin plate with a thickness less than 3 times the wavelength. The velocity of ultrasonic waves is determined by the elastic modulus, density, and Poisson's ratio of the material they travel through. The following shows three equations for the velocities of different types of waves. These include longitudinal wave, transverse wave, and surface wave. Attenuation is defined as the rate of decrease in energy when an ultrasonic wave propagates through a medium. Material attenuation depends on material properties. Below we can see the attenuation coefficient. If the attenuation coefficient is large, it means it is very hard for an ultrasonic wave to propagate through the medium, whereas if it is very small, it means it's very easy for the wave to propagate. There are several types of attenuation. The first is scattering, which is due to a change in the acoustic impedance by the presence of grain boundaries, inclusions, pores, or grain size. Absorption, which occurs because of the heating of materials, dislocation dampening, or magnetic hysteresis. Dispersion, which occurs because of the frequency dependence of the propagation speed. And transmission loss, which is due to surface roughness and coupling mediums. Diffraction, which can be defined as spread of energy into high and low energy bands due to the superposition of the wavefront. Here we see two types of diffraction, near field and far field. In these equations, little d is defined as the field length for either near field or far field. Big D is defined as the diameter of the transducer used in these experiments, and lambda is defined as the wavelength. To measure the spreading angle of the beam, we see that sine theta is equal to 1.2 times the wavelength over the diameter of the transducer. Acoustic impedance is the resistance to the propagation of ultrasonic waves through a material. The impedance is defined as Z, which is a function of density times the acoustic velocity of the material. These are given for any material and only depend on that material's properties. Here we see that the reflection coefficient, showing how much reflection occurs, and the transmission coefficient of the wave, showing how much of the wave is actually transmitted through a material, are both functions of the impedance. Therefore, they are also functions of the density and the acoustic velocity of the two mediums. The reflection and transmission coefficients can also be related to Snell's law, which says that the ratio between the acoustic velocity of one medium divided by the other is equal to the sine of the angle of incident divided by the sine of the angle of reflection. Here we can see how the reflection coefficient and transmission coefficient relate to these properties. The total refraction angle is a function of the two mediums' acoustic impedance and the two mediums' densities, as well as the acoustic velocity of the medium through which it's refracted. When two longitudinal waves are incident at the boundary between two materials, A and B, two reflected beams will be obtained. This excites different types of ultrasonic waves, as can be seen in the image below. Ultrasonic waves can be produced by the two following methods: magnetostriction generator or a piezoelectric generator. In a magnetostriction generator, the magnetostriction effect is observed. Here a ferromagnetic rod like iron or nickel will be placed in a magnetic field that runs parallel to its length. This field will cause the rod to experience a small change in its length. This is called magnetostriction effect. This change in length, either increase or decrease, produced in the rod depends upon the strength of the magnetic field, the nature of the materials present, and is independent of the direction of the magnetic field applied. In the diagram is the layout for a magnetostriction oscillator. It has a ferromagnetic rod in the center, a variable capacitor C to control the strength of the field, and two coils, L1 and L2, wound in different directions around the rod. One of the principles behind the magnetostriction effect is that when a high-tension HT battery is switched on, the collector circuit oscillates with a frequency. This frequency is defined as 1 over 2 pi times the square root of the length of the coil and the capacitance. The alternating current flowing through the coil L1 produces an alternating magnetic field along the length of the rod. The result is that the rod starts vibrating due to the magnetostrictive effect. The rod's frequency of vibration is given as a function of the length of the rod, the Young's modulus of the rod, and the density of the rod. The capacitor used here is adjusted so that the frequency of the oscillatory circuit is equal to the natural frequency of the rod, producing resonance. Now the rod vibrates longitudinally at its maximum amplitude and generates ultrasonic waves of high frequency on both ends. Some advantages to the magnetostrictive motor are its simple design, low production cost, and at low ultrasonic frequencies, the large power output can be produced without the risk of damage to the oscillatory circuit. A few disadvantages are it has a low upper frequency limit and cannot generate an ultrasonic frequency above 3000 kHz or 3 MHz. The frequency of oscillations depends on temperature, and there will be losses in energy due to the hysteresis and eddy current. Piezoelectric generators. Piezoelectricity means pressure electricity, which is used to describe the coupling between a material's mechanical and electrical behaviors. The word piezo comes from the Greek word pies, meaning squeeze. The piezoelectric effect is when a piezoelectric material is squeezed or stretched, an electric charge is generated on its surface. The inverse piezoelectric effect is when it's subjected to an electric voltage. A piezoelectric material mechanically deforms. Piezoelectric materials. There are several types of piezoelectric materials, one of which is piezoelectric ceramics, which includes barium titanate and lead titanate zirconate, or PZT, the most widely used piezoelectric ceramic. For these materials, the composition, shape, and dimensions of piezoelectric ceramics can be tailored to meet the requirements for a specific purpose. There are also piezoelectric polymers, such as PVDF film, and piezoelectric composites, which combine piezoelectric ceramics and polymers to attain properties which cannot be achieved in a single-phase material. Below is the circuit diagram for a piezoelectric oscillator, the properties of which are explained in the following slides. The principle behind this oscillator is as follows. When the HT battery is switched on, the oscillator produces high-frequency alternating voltages with a specific vibration frequency. Due to the transformer action, an oscillatory EMF is induced in the L3 coil. The high-frequency alternating voltages are fed onto plates A and B. The inverse piezoelectric effect will take place, and the crystal contracts and expands. The frequency of vibration is given below. The variable capacitor C1 is adjusted such that the frequency of the applied AC voltage is equal to the natural frequency of the quartz crystal, allowing resonance to take place. The vibrating crystal produces longitudinal ultrasonic waves of large amplitude. Advantages are that the ultrasonic frequencies go as high as 500 MHz. The output of the oscillator is also very high, and it is not affected by temperature or humidity. The disadvantages is that the cost of a piezoelectric quartz is very high, and shaping the quartz crystal can be very complex. What are the applications of ultrasound? These include detection of flaws through non-destructive testing, or NDT. The principle here is that ultrasonic waves are used to detect the presence of flaws or defects in the forms of cracks, blowholes, porosity, and etc. in the internal structure of a material. By sending out an ultrasonic beam and measuring the time interval of the reflected beam, flaws in the metal can be determined. Below is the block diagram from an ultrasonic test instrument. The most important pieces here are the screen that allows us to find where flaws and defects are inside the workpiece by using the probe, which fires and collects the ultrasonic beam. Here we see the principle behind the wave reflection at a flaw. The probe fires a beam into the workpiece, which is then reflected back to the probe itself. When the wave passes through the workpiece, we can see that it is distorted because of the flaw. In plate testing, an initial pulse is fired into the plate at one intensity level, and the backwall echo is returned at a different intensity. If a flaw is detected, it will come back with a different intensity from the other two, and its location can be determined this way, by comparing the differences. Wall thickness, due to corrosion, can be determined similarly by scanning around a circular surface and seeing how long it takes for the reflected beam to return. Through transmission testing allows locations of flaws to be determined by comparing the intensity of a transmission signal that goes all the way through a workpiece to that of one that hits a flaw. By using the sound path and probe angle of a beam fired into a weld piece, the depth where lack of fusion occurs inside of a weld can be determined using a series of simple calculations. Many of the tests described are called straight beam inspection techniques. These allow for direct contact, either through one or two elements, those with a fixed delay, by using through transmission, or immersing the workpiece and the probe inside of a fluid. Another use for ultrasonics is in ultrasonic drilling, which allows holes to be made inside of hard materials such as glass or diamond. For this purpose, a suitable drilling tool bit is fixed at the end of a powerful ultrasonic generator. A slurry is placed around the drill bit and the plate where the hole is to be made. An ultrasonic generator causes the tool bit to move up and down very quickly, and the slurry particles below remove the material from the plate. This process continues until a through hole is drilled.
这个60还大，不过一会儿得做一个腰部的，然后把这个平衡。这次做的重点是
Some metals that cannot be welded by electric or gas welding due to temperature requirements can be welded at room temperature using ultrasonic waves. In an ultrasonic welder, a horn vibrates ultrasonically and presses two pieces together very rapidly. This is known as a cold welding process.
Ultrasonic welding. Ultrasonic welding is a welding technique where a solid-state weld is created by high-frequency ultrasonic acoustic vibrations on the workpieces held together under pressure. Ultrasonic welding is basically carried out to join two plastic workpieces. For this, let's consider the welding setup as: connect the setup with the electric power supply, and place two plastic workpieces on the anvil and below welding setup at its right angles. Now let's understand how the welding process is carried out. First, switch on the electric power supply. We see that transducer attached to the electric power supply changes the electric signal to the mechanical vibrations. These vibrations are then transmitted to the converter, booster and horn. All of these then work together, due to which the horn oscillates after receiving the vibration. Now bring the horn in contact with the upper plastic workpiece. We see that the vibrating and oscillating horn applies a pressure on the workpiece, which is held tightly by the anvil. Now apply this pressure for a fixed amount of time, which is called as weld time. Due to pressure, a frictional heat is developed between the plastic workpieces. Hence, the plastic of workpieces present at the interface area melts and flows into each other. Now hold the horn for some time over the workpieces so that proper fusing of melted plastic takes place. This time period is called hold time. Now once the melted plastic solidifies, remove the horn over the workpieces. Thus we get the welded workpieces as ultrasonic weld. Some of the examples of ultrasonic welding: Related terms are
ultrasonic soldering. For metals like aluminum, which cannot be directly soldered, they can be soldered using ultrasonic waves. An ultrasonic soldering iron consists of an ultrasonic generator with a tip fixed at its end, which can be heated by an electrical heating element. The tip of the soldering iron melts solder on the aluminum, and the ultrasonic vibrator removes the aluminum oxide layer. Ultrasonic cutting and machining. Ultrasonic cleaning is an inexpensive technique for cleaning machine parts, electronic assemblies, armatures, watches, and etc. Ultrasonic sonar can be used to detect items underwater. The method consists of sending a powerful ultrasonic beam in a particular direction through a body of water. Noting the time interval between emission and reception of the beam after reflection, the distance of the object can be easily calculated. The change in frequency of the echo signal is due to the Doppler effect. It helps determine the velocity of the body and its direction. By measuring the time interval between the transmitted pulse and the received pulse, the distance d is equal to Vt over 2 between the transmitter and the remote object is determined using this formula, where v is the velocity of the sound in seawater. Sonar has a wide range of applications, including locating shipwrecks, submarines, fish finding, and doing seismic surveys.
In this video we'll be talking about sonar. Now sonar is the use of sound to see through water. This technique has been used by whales and dolphins for millions of years. We've now taken it and made a form of technology which allows us to do the same. In the image before you we have one variation of how sonar can be used. So you have a ship which has a transmitter and a receiver on it. Now the way it works is that we send out a pulse or a ping. As you can see, it will go down in a single direction. Now the speed of sound is constant, so it stays the same, it doesn't change. So we can actually time how long it takes to go down to the bottom, bounce off an object, and head back up to the receiver. So once we have the time, we divide it by 2, since there's a signal going down and a signal going up, and we'll find out what the depth to the bottom of the sea is. Now that's okay with a situation where the seafloor is nice and flat, but what about if we have an object? So we'll create an object. Okay, here we have a nice rock, and we're going to send a sonar signal down towards it. So the transmitter will send out its ping. Make it nice and big so it's nice and clear, and will eventually hit the object. Now when it hits the object, the areas which are closest to the signal will bounce off first, and those which are further in will go last, and those which are furthest away will obviously take the longest before they start bouncing back. And the end result is we'll get a nice reflection which looks like the rock. And that's the signal that will bounce back. So we get a bent or a disturbed signal back, and this allows us to take a 3D image of the object on the ground. Now, we don't just send a single small pulse down, we actually sweep across a large area. So as you can see with this ship, it actually does a nice large space or arc as it travels back and forth. And this means that it can actually search quite a large area as it's traveling back and forth. So you can see here it's an artificially coloured chart where the hotter colours are shallowest, as up here. And all of a sudden we have a cliff going down, and as the cliff drops, you can see it going into the cooler colours, and it goes down deeper and deeper. And this ship will travel back and forth through the ocean, mapping it out. Now, oops, went too far. Here is a good example of such an area. So this has been mapped out and then artificially coloured to make it easier to see. You can see over here there's a really nice shallow area, so the hotter colours again show the shallowest area, and as it goes to the cooler colours, for the oranges, the yellows, then into greens, and then finally the blues and violets, it becomes deeper and deeper. And you can see features such as cliffs along here and here, and there's even a small readout which is poking out there. And over here we have a key which shows us what depth each colour represents. Now, we don't only use it for these general things. We can also map out things such as this rift. Now, this is exactly what we were discussing when we talked about the mountain range in the Atlantic where the cable first came across. So when they were laying the cable back in the 1800s, they actually came along and they reached this, and they had to go up and over it, and then it sort of dipped into here a little bit and then came up and back down it. And this is how they discovered, so they actually were measuring the depth of the ocean as they travelled, and that's how they discovered this mountain range. And little did they know that this range actually travelled all the way from the North Pole to the South Pole. Now, we actually still have cables running across this ridge, and every now and again, as we have movement of the tectonic plates, it will snap in these areas and have to be repaired. Now, that's the natural features which we have, but mankind's been littering the ocean for many, many years, especially in the last 100 years as we've had lots of wars. And here are a few things which have been discovered since. So as they've mapped around, one of the most famous ones is this one here. For those that you don't know, this is the Titanic. And it was done through finding out, first of all, what its course was, and then finding out approximately where it would be, and then they used side scanning sonar to go back and forth, and they found the Titanic. And what we have here is the actual ship. Now, what I'll show you first is how it looks like from the scanner. So you can see the lines travelling up and down as the sonar travelled back and forth. And over here we have the back of the ship, and over here we have the front of the ship, and they're actually a couple of kilometers apart because it broke up near the surface and then floated away down as it headed down to the bottom. And what we have here is, if you look really carefully, here we have the bow of the ship, and you can see the bridge through here, and then 1, 2, and a little bit of the last funnel towards the back here, and around here is where the ship broke down. So it's a really clear image. Other images which we have, this one here is the Britannic, which is a sister ship to the Titanic. You had the Britannic, the Titanic, and the Olympic. This one here was used as a ship during the war as well, and you can see through here a hole where it was torpedoed and it sank in fairly shallow water. And this is a scanning radar of this. This ship here, the HMS Royal Oak, is a battleship from the Second World War. It has the dubious honour of being the very first battleship which was sunk during the Second World War. And this is a scanning image which they've got of it. And up here, this is actually a German bomber which was sunk in the English Channel during the Battle of Britain, and it was discovered again through side scanning radar. There are hundreds and hundreds of wrecks in the English Channel, and this is one of them that was picked up. This particular plane here has actually been raised since, and is now sitting in one of the maritime museums in England. So that is a quick explanation of how sonar works. For the next video, we'll be talking about seafloor spreading and the development of tectonic plate theory.
Ultrasonics also have many medical applications, including diagnostic sonography, or medical sonography, which is an ultrasonic-based imaging technique that allows us to visualize muscles, tendons, and pathological lesions, providing an idea of the structure of the human body. They also are used to visualize the fetus during routine and emergency prenatal care. 3D ultrasounds allow us to see babies developing inside of a mother's womb and get an idea of the baby's shape, size, and general properties. Another use of ultrasound is in ultrasound therapeutic applications, wherein malignant tumors and other disorders can be treated using either focused ultrasound surgery or high-intensity focused ultrasound. These procedures generally use lower frequencies than medical diagnostic ultrasound, but with significantly higher time averaged intensity. If you'd like to learn more about ultrasound, or barolytics, or frequency control, please go to the following website at www.ieee-uffc.org/ultrasonics. Some of the information is openly available, and some of it will require an IEEE UFFC Society membership. To join, please go to the following website at www.ieee.org/join. For more information on electrical engineering, computer science, or any other sciences and related topics, please visit IEEE's Electronic Library by following the link below.